my pleasure to welcome all of you to the new session of the bank seminar. And today it's a pleasure to come with Robert McCann from the University of Toronto, and he will talk us about a geometric approach to regularity of optimal transport maps. So please go ahead.
Okay, thank you. I'm happy to be here and see some old friends, at least virtually. So I thought that I'm going to talk about joint work with Simone Brendel and Vivian Leger and Cale Rankin from which appeared in Krella's Journal in 2024. And it's also based on older work that I did with Young-Hyun Kim and Micah Warren back in 2010. And I thought it was an appropriate topic for the Bang seminar because it's going to bridge analysis and geometry. So this is my and there's a version of the slides on my, so you see my website in red there on the slides. And if you click on the talk link, there's a version of these slides there in case something goes by too quickly. So I'm gonna, here's the outline of the talk. I'm gonna remind you of some things about extremal surface theory. And then I'm gonna kind of give a crash introduction to optimal transport. And particularly emphasizing some of the differential geometry and topology and links to curvature. And then I'm going to try to tie the two subjects together. So this part's super classical, probably especially for this audience, but bear with me. So let me see, and let me make sure that I want to be able to annotate. So hopefully I can annotate on these slides. Good. Except let's do it in red. And now I can maybe remove this. So here I wrote the, the basic sort of graphical form of the plateau problem where I'm minimizing the surface area of the graph of a function u subject to some boundary conditions on a domain omega. And, this is a pretty old problem in the calculus variations. And here's the Euler-Lagrange equation for it. And if you blow up geometrically around the graph with the right scaling, then what you get is a minimal graph on the underlying space of n variables. Omega here is supposed to sit in Rn. And if you're in low enough dimension, less than 7, then it's famous results of Bernstein in 2 dimensions and DeGiorgi, Almgren, and Simons in higher dimensions that the only solutions to this equation in the entire space Rn are linear solutions. And then if you go to higher dimensions, you get these counterexamples based on Simon's cones that were shown rigorously by Bombieri, DeGiorgi, and Giusti to be minimal. And then there's also the higher codimension case of this, which Federer studied already back in 1969, around the time I was being born. And showed that when you have, say, an algebraic curve or an analytic variety, it actually satisfies the higher codimension version of this equation in Cn. And so the regularity theory, somehow because of this, you have a nice regularity theory if you're in low enough dimensions, and then if you're in higher dimensions, you have counterexamples to regularity. And in codimension 1, the counterexamples are in you have to go to dimension 7 or higher. But in higher codimension, you can have codimension 2 singularities, just like algebraic curves have isolated singularities in the plane. And then there's the big regularity theory of Almgren that was posthumously published, which establishes this regularity outside of codimension 2 singularities. And okay, so this is a very well-known story, minimal hypersurfaces in Rn plus 1. Maybe less well-known story is if you take, so the integrand here is something like square root of 1 plus, I don't know, let's call it v squared. And if you take the Legendre transform, this is a convex function, its graph is a hyperbola. Sorry, it's asymptotic to a light cone. If you take the Legendre transform of this, you get minus square root of 1 minus p squared, p being the Legendre conjugate variable to v, which is the graph of a semicircle. So it jumps to plus infinity outside the unit disk. And if you take that as your integrand, I didn't put the minus sign here, so now I'm maximizing instead of minimizing. And you also, again, look at something like a Dirichlet problem for maximizing this integrand. What you're essentially doing, you've changed the sign of the underlying metric from a purely spatial metric to a space-time metric. So you've somehow you can think of this as Lorentzian geometry in n+1 variables. And when you perform this maximization, what you're doing is you're trying to look for a volume or an area maximizing hypersurface in n+1 variables. But the the gradient u squared had better be less than 1 for the integrand to make sense. And so your hypersurface is you're asking to find a spatial surface, spatial hypersurface of maximal area. But you can do the same thing if you take a maximizing solution and blow up around it. And as long as the slope is strictly less than 1 at the point where you're blowing up, then you will get a solution to this Euler-Lagrange equation, and it holds throughout all of Rn. And it turns out that the regularity theory for this is, in some sense, almost nicer than the regularity theory for minimal surfaces, because there's this theorem that was proved up to 4 dimensions by Calabi and in all dimensions by Cheng and Yao in these classical works. That said, and maybe I have the year wrong on Calabi, maybe it's even earlier. That says any entire solution to this equation here in Rn, provided its slope is less than 1, is linear. So you have an even better Bernstein theorem than in Riemannian signature. And the pros are that this holds for all dimensions, but there are also some cons. And the cons are that the unit sphere in Lorentzian geometry is non-compact. And so the symmetry group is non-compact, and that causes some problems. And then also the ellipticity of this equation degenerates when the value of the gradient approaches 1. And so if you want to try to prove a regularity theory for these things, then the hard part is to show that the gradient stays bounded away from 1 when you do the blow up, or that you're looking at it. So the problem points are the points where the gradient is not bounded away from 1. And then there are some orientation delicacies associated with disconnectedness of the zero sphere. And you, like Almgren and Federer, you can ask, this is sort of the maximal surface problem in codimension 1 space-time. You can also ask what happens in a metric of signature other than time-like directions, several space-like directions, and a lot less is known. So there was a PhD student of Reese Harvey who wrote a thesis on this in 1991, which was surveyed in a work of Harvey and Lawson in 2012, Jack Mealy. And but so for me, this is actually a quite interesting case, the case of signature NM, because at least when m equals n, it arises rather naturally in optimal transportation. And so this was somehow a very surprising discovery that I made 15 or 16 years ago with Young-Han Kim and Micah Warren, that if you take the graph, so when you study the Monge-Kantorovich optimal transportation problem, you have say a domain omega, and you're mapping into a range omega bar. And so you have some cost function, C, or maybe that depends on a variable in omega and a variable in omega bar. And sometimes you minimize cost, sometimes I prefer to maximize benefit. I claim that you can put a metric on the product space here of omega across omega bar, that you can use the cost to define a metric on the product space, such that if you have some density down here, I guess mu, or an n form, and an n form up here, mu bar, when you try to pair them in the optimal way possible so as to minimize this cost or maximize that benefit, I mean, under reasonable conditions in the cost, you hope to get an optimal map. And I claim that this optimal map is actually a zero mean curvature n-dimensional submanifold of a 2n-dimensional space. So these domains are both n-dimensional here in the picture that I'm trying to draw. And so there's this unexpected link between this optimal transportation problem of Monge and Kantorovich and the plateau problem in a strange signature. And then the more recent development that I'm also going to talk about is this work with Brendel, Leger, and Rankin, where we show that in this signature NN case, a sign becomes favorable relative to the Riemannian background. And so this somehow reflects what Cheng and Yao and Calabi showed, that regularity is actually in some sense better. And so it's going to allow us to give a new proof, at least of the interior regularity theory of Mott, Schrödinger, and Wang for optimal maps. And by exploiting this connection with the plateau problem. Okay, so I'm actually gonna talk about theorem 2 first, and then come back and talk about theorem 1. And so somehow this is the heavy lifting, theorem 2. There's this little bit of differential geometry that I'm going to do. So it's an exercise in submanifold geometry. And so I need to establish a bunch of notation. So I'm going to have this ambient space, and the ambient objects will always have the hat on them. And it's going to be n plus m dimensional with a signature nm metric g hat. And then I'm going to be looking at, and the g hat will have a Riemann tensor r hat. And I'm going to be looking at space-like submanifolds, which are n-dimensional, call them sigma. And the restriction of, I want to erase this one. The restriction of objects in the ambient space to the submanifold will appear without the hat. So when I restrict g hat to the tangent space, I get a g without the hat. That's positive definite. That's what it means for the submanifold to be space-like. And I'm going to be interested in maximal submanifolds in the sense that their mean curvature vector vanishes. And where the mean curvature is the trace of the second fundamental form. And the second fundamental form is this gadget that measures the difference between covariant derivatives in the ambient space and covariant derivatives on the submanifold, where the vector fields x and y are tangent to the submanifold sigma. So when I have this submanifold situation, one of the basic observations is the following lemma. So I'm now going to equip my ambient space M with an auxiliary positive definite metric as opposed to the sign metric G hat. I'm going to call the positive definite guy S, capital S. Its restriction to the submanifold will be S without the hat. And then the claim is that there's this constant independent of the submanifold such that when I take the G Laplacian of S and divide it by S, I have a lower bound in terms of a partial trace of the ambient Riemann tensor and then some multiples of the orthogonal directions EL to EN. So these objects are in direction EN, and then I get a partial trace over all the orthogonal directions. And okay, so this is a long calculation, and I'll try to give you a flavor for it. But anyhow, the point is that the constant in this inequality is independent of which submanifold we're looking at. Maybe I should even go, before that, I'm going to even go back a slide and tell you something about the optimal transportation thing in this picture I'd drawn. So just like in the Chang-Yao-Calabi theorems, when we want to talk about the smoothness of this graphical object, the hard part is going to be showing that it's not tangent to the vertical or the horizontal, so somehow bounding it, what was gradient of u in the Chang-Yao examples. So we'll come back to that. And this lemma that I just stated is going to be useful for doing that. So here's a proof sketch for the lemma. So you do a long computation, you throw away a bunch of terms that vanish because it's a maximal surface. And then you get that the G Laplacian of S is related to a bunch of things, but there's this crucial sign distinction here, which is that because S is a space-like submanifold and it's space-like of maximal dimension, all of the orthogonal vectors to S are time-like. And so G hat of the second fundamental form, which is orthogonal to, so this is pi if you like, orthogonal to the submanifold sigma, this time it has the right sign for bounding below, and that's going to be this inequality up here. And so I can throw away the red term. That's helpful. And terms like this are good because they have a helpful sign. Terms like this, they're a mixture of, so the second fundamental form appears here, but I can control it using sort of Cauchy-Schwarz with epsilon in terms of, a large multiple of this and a small multiple of that, maybe changing the sign on this guy. And terms like this are bounded below by the S magnitude of En and the S magnitude of El, up to some large constant that reflect the fact that all norms on Euclidean space are equivalent. And so I get this this inequality here, where I keep this term, I throw away this term, I keep this term, and all the other terms I bound in terms of some enormous constant times a product of S in the direction En and S in the direction of El. And then if you bring this term over to the other side, you get the inequality that I had on the previous page, and um, sorry, let me go back to it. So if you bring this term over to the other side, you get this inequality with this large constant, and that tells me that if I know the sign of the Laplacian, for example, if I'm at if En is a local maximum for S, so the sign of the Laplacian is negative, then it tells me a lower bound on S in terms of R. And here is that lower bound. S in the En direction is lower bounded by R, by this partial trace of R with this large constant C. But the C is independent of the submanifold. And so this is going to be a corollary which we're going to leave alone for a while, but it's an absolutely crucial corollary. So does anyone have any questions?
Yes, ma'am. A question
Oh,
concerning can you hear me?
sorry?
Can you hear me?
Yes, I can hear you.
So I have a question about the formal frame. You take any S
Yep.
as a dictates of you,
I'm sorry, what about it?
and you diagonalize the S.
Yeah. So
Locally.
yeah, the little ENs diagonalize S, and the big E hats, which perhaps appeared in the proof, they diagonalize G hat.
No. Does it mean this is only a local argument?
Yeah, this is local.
I'm not even for any point. This is true. Not any two symmetric tensor.
So we're going eventually.
Only for open dance subset of the manifold.
Yeah, eventually we're going to. In fact, so if you think about the story that I told you with optimal transportation, we're working on those. That's going to be a story that, I mean, you could do it on manifolds, but you can also do it on Rn. You can do it. The domains omega and omega bar can be subsets of Rn, and then you have global coordinates.
Thank you.
Okay. Other questions? Okay. So now I'm going to switch gears and I'm going to talk about optimal optimal transport. So I'm going to be trying to maximize this benefit function, which is a subject of x and y on a pair of, or x and x bar, I guess y is x bar, on a pair of manifolds of the same dimension, omega and omega bar. And those are going to be the landscapes in which my transportation takes place. And then I'm going to have an n form on each of the two landscapes, which are actually going to be normalized densities of supply and demand. So these n forms are going to have densities with respect to the sort of canonical orientation on the subdomains, and the integral, the total mass of mu and mu bar can be normalized to v1, and I'd like to normalize it that way. And so Monge's problem was you look for a mapping from omega to omega bar, which pushes forward the first normalized measure to the second normalized measure. And among such mappings, you try to maximize B. And Kantorowicz's contribution was he realized that he had several insights, but he realized that this problem can be reformulated or is closely related to a linear program. And here's the dual linear program, which is a minimization. So basically, you introduce Lagrange multipliers u of x and u bar of x bar for the mass constraints on. So I drew a picture before of graph of f, but I can also think of f as a joint measure sitting on the product space omega cross omega bar. And these are, but the marginals of this joint measure sitting on the product space are prescribed. They're mu and mu bar. And these guys are the Lagrange multipliers for those two marginal constraints. And then you try to minimize the expectation of u against mu and the expectation of u bar against mu bar under the constraint that the sum of these two guys has to dominate the benefit of pairing x with x bar in this maximization problem. And then the numbers you get, the supremum is equal to the infimum. That's Kantorowicz's theorem. And so on this side, it looks like linear programming. On this side, it looks like some bad nonlinear variational problem. And but if the bad nonlinear variational problem happens to have a smooth solution, then and if the solution is, say, a diffeomorphism between omega and omega bar, then what this constraint, the push forward constraint, is doing is it's prescribing the Jacobian determinant of that diffeomorphism. So when you have a smooth solution here, the Jacobian determinant is going to measure the ratio of the density of supply at x to the density of demand at f of x, up to a sign because of possible orientation issues. Okay. And so one can also think of the graph of f in terms of the submanifold. So if I were to write this inequality in the form u plus u bar minus b is bigger than 0, you can also think of the submanifold. You have a non-negative function. You can think of the submanifold where equality holds, and that submanifold is going to contain graph of f, or support of gamma in the case of a joint measure. So it's not true for all b's that you'll have an f. And so this is the problem that it took quite a while for one to have conditions that actually guaranteed that the f will be a diffeomorphism, exists and is a diffeomorphism. And for the special choice of benefit b of xy equals x dot y, or equivalently, the cost, because the marginals are constrained, the cost c equals 1/2 x minus y squared. Regularity theory was developed in 2 dimensions by Delanoë and in higher dimensions by Caffarelli and Urbas in the 90s. And there were also versions in the late 90s for other special choices of cost. But the first theory of regularity for an open class of costs was this result of Ma, Schrödinger, and Wang from 20 years ago. And so they said, let's assume B is 4 times continuously differentiable, and that for every x, the mapping that takes x bar to the differential of B with respect to x should be a diffeomorphism. And they want its range to be convex for each x. And then then they said, well, suppose you have a curve whose image under this diffeomorphism is linear. So the second derivative of the curve under the diffeomorphism should be 0. They call that a B segment. And then they ask that whenever you have a pair of curves, xs in the domain and x bar t in the range, which form a B segment when s is 0, then if the mixed partials of B are 0, the mixed second order partials of B are 0, they asked for the mixed fourth order partials of B to be positive. And they call this condition A3, or sometimes A3 strong. And then if you only have non-negative here, they call that A3 weak or A3 closure. Okay, so actually under hypothesis A and B appeared earlier, and what Ma, Schrödinger, and Wang really added to the story was A2 and A3. And so somehow A0 and A1 already appear in the habilitation of Gangbo in 1995 and this work of Levin, from which maybe I have the date wrong, maybe it's 1999. But under hypothesis A0 and A1, a unique minimizer F will actually exist. So you could look at joint measures that have marginals mu and nu, but under this hypothesis, almost every x will correspond in that joint measure will correspond to a single y, and so you can reconstruct the measure as a map. And it pushes forward the first guy to the second guy in the sense of just a Borel map. There's a notion of push forward for Borel maps. And so we don't yet know F is smooth. And then Ma, Schrödinger, and Wang tell us, if in addition A3 and A2 hold, by the way, part of A3 was that I want the situation to be symmetric under interchange of x and x bar. So if B star also satisfies A0 to A2, then Schrödinger, Ma, and Wang tell us that if the densities of mu and mu bar are bounded above low and smooth enough, then the map will be actually as smooth as the densities, and even one derivative is smoother. And somehow what's going on here is that if I think of the determinant of df equals rho over rho bar equation, rho composed with f, this turns out to be related to something involving the Hessian of the Kantorovich potential U, which we'll write down in more detail later. And so more or less, this is going to be a kind of very nonlinear elliptic equation, kind of like the Monge-Ampere equation in the simplest cases. And when the ellipticity becomes uniform, then you should expect U to inherit smoothness from rho and rho bar. And so U should be two derivatives smoother than rho and rho bar in the best case, and F should be one derivative smoother. And that's their theorem. And there were a lot of improvements and related results by many authors. One of them is by Lopere that's worth mentioning. So Lopere, for example, was able to lower this to the case k equals 0 and say if the densities are just bounded above and below, then F is still Holder continuous. And he also showed that if the closure of A3 fails, then you can find smooth bounded densities for which F has discontinuities into it. And so A3 is almost necessary and sufficient to have a regularity. It's necessary and sufficient in this strange sense that, if A3 holds, then for every rho and rho bar, you have a smooth map. And if A3 bar fails, then there exists a rho and rho bar for which you have a discontinuous map. And so the first thing I want to tell you about is this older work with Kim and then with Kim and Warren, which kind of geometrizes these mysterious conditions of Ma, Trudinger, and Wang. And so our point of view is it's going to start with this Kantoorovich's idea that it's useful not just to think about the map F, but about the joint measure, which is the image in the product space of mu under the identity cross F. And that thing will always exist even when maps don't exist. So a measure with these marginals that you want, mu and mu bar. And if you think of the support of that joint measure, call that sigma, and you define this function of four variables, which I call the cross difference, but it measures the benefit of pairing x with x bar plus the benefit of pairing x naught with x bar naught minus what happens if you exchange partners. You would expect that if gamma is an optimizer in the Monge-Kantorovich problem, this function of four variables should be non-negative whenever both x bar and x naught x bar are in the support of gamma, representing the fact that it was really efficient to pair with x with x bar and x naught with x bar rather than the opposite. And so now if I think of this function of four variables as I think about fixing x naught and x bar naught and just varying x and x bar, so now I have a function of two variables. That function of two variables is non-negative, and it's zero when it's non-negative on sigma cross sigma, and it's zero when x bar equals x naught x bar. So let's Taylor expand it around x naught x bar naught. And so because the function vanishes, the zeroth order term vanishes, and because of this minus sign here, when I Taylor expand this non-negative function around its minimum, in this product geometry, the first order terms in the Taylor expansion are going to vanish, and part of the second order term in the Taylor expansion is also going to vanish because, for example, if I take two x derivatives with respect to b here and here, and then set x equal to x bar, they're going to cancel each other. And so even at second order, so you have the Hessian of delta naught at this point where you Taylor expanded. But even at second order, it's only the mixed partials of B with respect to the two variables that appear in this Hessian. And so I can think of this Hessian of this function of two variables as being a pseudo-Riemannian metric tensor on the product space. And it's non-degenerate because of hypothesis A1 of Ma, Trudinger, and Wang. But it has the property that if I flip the sign on delta x and keep the sign on delta x bar and keep the sign on delta x, because of the second formula, I will change the overall sign, and that means that this metric tensor I've just introduced is signature nn. So that's my n time dimensions and space-like dimension metric. And the fact that this guy's non-negative tells me that when I restrict this NN metric tensor to the submanifold sigma, which turns out to be always an n-dimensional Lipschitz submanifold, by work that I did with Warren and Pass, also about 15 years ago, then at least the restriction is non-negative. So it's non-time-like. And it turns out that all the hard work in proving a regularity theory for this submanifold is to show that this non-negativity becomes strictly positive. So somehow that uniformizes the ellipticity in the Monge-Ampere type equation. And once we have strict positivity there, things will be smooth. And so showing that this non-negativity becomes strictly positive is exactly what Ma, Trudinger, and Wang were able to do under these additional assumptions on the densities rho and rho bar and under hypotheses A2 and A3. And the story that I'm telling is particularly simple in the case of the bilinear benefit function, because then the cross difference is something, bilinear, and that this metric that I'm talking about is flat. It's has these n by n blocks, which are 0 in the diagonal, and the n by n identity matrix off the diagonal. And more generally, the matrix looks like this. Okay, so another observation that I made with Kim back in 2010 was that the second hypothesis of A2, which was that the dxb of x comma omega bar is convex, this is actually a statement of geodesic convexity of the slice x omega bar in the product geometry with this Hessian metric. And since we've asked for symmetry and interchange of x and x bar, I'm also going to ask that these guys be geodesically convex for each x bar in the product geometry. And the other thing to notice is that if I take a tangent vector to either this horizontal or this vertical subspace, its inner product with itself is 0 for this metric. So this cross that I've drawn here is kind of the light cone for this signature NN metric. And when we look at our graph of our optimizer, what we're asking if we want smoothness is that its tangents stay away from these n-dimensional light cones. Questions? Okay. So far, this Hessian metric that I've put on the product of omega cross omega bar, it only depends on the function that I'm optimizing. I haven't used the densities rho and rho bar or the n forms mu and mu bar at all. And we're going to get to those in a moment. But also in my work with Kim, what we observed is that when A0 to A2 hold, then this funny condition of Ma, Trudinger, Wang about positivity of certain fourth derivatives along certain curves is actually a sectional curvature condition on the metric associated to H. And it says whenever you have a horizontal vector P and a vertical vector P bar, so let's say P plus 0 and 0 plus P bar, their condition A3 is asking for sectional curvature positivity in the two planes spanned by these two vectors whenever they're orthogonal to each other. Great. And so far, as I say, the metric that I've introduced only depends on the cost function or the benefit function B. What Warren added to this story was, in our collaboration with Warren, was that let's now put a conformal factor in front of the metric H bar, and let's choose the conformal factor so that the volume associated to this conformal equivalent metric is up to sign the wedge product of the n form mu and the n form n bar. So now I've taken the densities into account and not just the cost. And the theorem is that then if I take one of these B optimal joint measures on the product space, its support will actually be volume maximizing among homologous things for this conformally equivalent metric. And so this makes this unexpected connection between the optimal transport problem and the plateau problem for codimension n space-like surfaces of an 2n-dimensional space with pseudo-Riemann with a split signature. And moreover, so now we have that our rectifiable submanifold has zero mean curvature with respect to this conformally equivalent metric. And moreover, I gave these nice characterizations of condition A3 and A2 in terms of the geometry of H. They work equally well for this conformally equivalent metric. So this realizing A3 as a sectional curvature condition works with G hat instead of H hat, and realizing A2 as a geodesic convexity statement works also with G hat instead of H hat. And I want to sort of sketch the ideas that go into this proof that the B optimality of gamma implies that the support of the optimizer is volume maximizing for this metric. And it's a calibration argument. So this is somehow this technique that was pioneered by Harvey and Lawson in the early 1980s. And so the idea is I have my optimal object, supportive gamma, and I want to think about deformations of it. And I want to say that this guy, if these are local deformations or compactly supported deformations, then sigma has larger volume. And so in order to do that, what I want to do is find an n form, phi, um, and it's very explicit. It turns out to be the average of mu into mu bar. And this n form is going to be its derivative is going to its exterior differential is going to vanish, and that's because somehow this is rho of x times the wedge product of the x's, and if I differentiate, if I wedge an x bar into here, I would take an x bar derivative of rho, but it doesn't depend on x bar, so that's why it's a closed form. And it turns out that exactly the average of mu bar has this kind of fascinating property that when I evaluate this on a simple n vector, what I get, the metric g hat was chosen so that what I get is bounded below by the g hat norm of the n vector. But equality holds on this thing here. And so now if I want to compare, if I have sigma and I want to compare it to sigma prime, because the form is closed, when I integrate phi over sigma, I get the same thing as when I integrate it over sigma prime. If they're homologous to each other. And on the other hand, because of this inequality, because I have equality on the tangent sigma prime, I get this is equal to the volume of sigma, and because I have this inequality in general, I get this term dominates the volume is sigma prime. And so that's what tells me that sigma is volume maximizing. All right. So now I'm kind of ready to, maybe I should have asked other questions on this. That it's a lot to absorb, I guess, if you haven't seen it before. So now I'm at the point where I can state this regularity result of Ma Trudinger Wang. But to talk about regularity, it's useful to have a reference metric. And so I could take it to be, say, the Euclidean metric on the domain. But I want to take, I'm going to just shut the door because I'm getting a phone call in the background. Sorry. So if you fix the Euclidean metric on the underlying domain, you need to carry it forward to the range or the codomain, omega bar, using the benefit function. So, and using the inverse matrix. And then you want to put a conformal factor in front of the range part, which again makes the volume form of S hat up to plus or minus the same as the volume form of G hat. And then what the interpretation of A3 in this setting is that there's this Riemann tensor in these orthogonal directions was positive and in fact can be bounded below by the S hat norm of this two-plane P wedge P bar. And there's some constant that's associated to the choice of S, kappa. And okay. And then the other thing is that this is going to be an interior regularity theory. So so far we can't say, although Trudinger and Wang in a subsequent work for optimal maps were able to show, under suitable conditions, we're able to show regularity of the optimal maps up to the boundary of omega. We're only going to be able to show regularity in the interior as they did with Ma. And so we're going to choose a test function, which is compactly supported, and we'll show regularity on the support of the test function. And the test function will be 1 on a large chunk of. Okay, and now this is going to be an a priori estimate. So the way their regularity theory works is that you first prove something when smooth maps F exist and solve the problem, and then you use a continuity argument to show that if you try to deform F from a smooth case to a non-smooth case, the set of deformation, so you interpolate between some smooth setting and some setting you want to know whether it's smooth or not, using a parameter 0 and 1, and this a priori result is going to say that the set of parameter values for which you have smoothness is closed, and an implicit function theorem is going to tell you that the set of parameter values for which you have smoothness is open, and so it must be the entire interval, closed interval 0, 1, and that's how you get smoothness at the other endpoint. So here's the statement of the a priori estimate. It says that under these hypotheses, there's a constant. It's the same constant from our lemma before, more or less, such that when I have this geometry of this, here's the submanifold in the product space. Again, the enemy was I want to prevent my submanifold from being tangent to one of these light-like horizontal or vertical fibers. And that is to say, when I take the ambient sign metric and I restrict it to the submanifold to get G, I want to be able to bound G below away from 0. That's what tells me it's not that things are not degenerating. The space likeness of G is not degenerating to light likeness. And that's exactly what this theorem tells me, at least in the support of a test function whose restriction to sigma will be called phi. So G is bounded below by a product of kappa and phi squared times S. And S was positive definite. It was this positive definite thing. Questions? And then after you prove this a priori estimate, as I mentioned, the regularity follows by doing local replacements using the continuity method, doing this interpolation argument and using this to show closedness and an implicit function theorem to show openness. And things are regular, so you pick a small domain and you try to replace the map on the interior of the domain subject to the same boundary conditions. And if the domain is small enough, everything's good enough to make the interpolation argument rigorous. So let me show you how the proof of this theorem works in this geometric framework that I've tried to set up for you. So the first step is that remember we had Monge's supremum integral b d gamma was equal to an infimum by Kenderovich of u mu plus u bar mu bar, where the relation u and u bar minus b had to be non-negative. And equality is going to hold here on the submanifold, the putative graph of the optimal map. And so if as long as f is smooth, as it was assumed to be in this theorem, I can differentiate everything. And the first order condition for this non-negative function vanishing is that the derivative of u minus the x derivative of b at f is 0. And the second order condition for this non-negative function vanishing is that the Hessian of u minus the second x derivative of b is bigger, evaluated at f is bigger than 0. But if I differentiate the first equation with respect to x, then I get something that looks much like the second term, except there's also an x dependence on f. And so I get a right-hand side, which involves the Jacobian of f and the mixed partials of b. So these were assumed to be non-degenerate as part of hypothesis A1, and which said that dxb was a diffeomorphism as a function of x bar. And the determinant of this Jacobian should be giving me the ratio of rho to rho bar, and in fact does give me the ratio under the smoothest hypothesis of the theorem that we're trying to prove. And so I see that the right-hand side of this, if I take log determinants, the right-hand side is now bounded because this is a diffeomorphism and this was assumed non-degenerate. And so that's good because it tells me that this inequality here has to at least be strict. And what we'd really love is for this inequality to be uniform. So we'd like to be able to put some multiple of, we'd like to say this is bigger than some multiple of S. And if we could get this uniform inequality, then this what that would be telling us is that this partial differential equation, which is a priori degenerate elliptic, becomes uniformly elliptic. And then the standard machinery of Gilbert and Schrödinger works, essentially. And maybe I should also mention that it's not an accident that this determinantal equation, which, by the way, in case, maybe it's nice to think about the case b equals x dot x bar, then these derivatives vanish, and this is the identity, and this is the ordinary vanilla Monge-Ampere equation, second boundary value problem, but still degenerate elliptic. And it kind of has to be degenerate elliptic because if you think, for example, if omega was a connected domain and omega bar had two disconnected pieces, any map between them is going to have discontinuities. And so you can't expect smoothness in all situations. And that's somehow what the hypothesis A2 is saying is no, you need to make the target domain convex. So in particular, it's connected, and then the densities have to be non-zero, because otherwise convex domain with a density that's one on two sides of a chasm and zero in the middle is as bad as a disconnected domain. And that would be, so for some funny choices of rho bar, I can make this equation degenerate. And so that's somehow the role of hypotheses A2 and A3 in this theory are to constrain rho and rho bar and the geometry of the domain through this convexity of its image under this map enough to uniformize the ellipticity of this operator. Okay, so now let's talk about why might it be uniformly elliptic. So since I'm trying to bound this expression below by a multiple of S, let me pick the point xf, which maximizes the largest eigenvalue of S relative to G. And I stick this test function in, but I imagine the test function being 1 on most of my domain and then maybe going to 0 at the boundary, because I want to use a kind of maximum principle and I can't control things well at the boundary. I want to have an interior maximum, and that's what the role of the test function. And then I take the Euclidean coordinates that diagonalize the matrix that appeared under this determinant. And let me put a copy of the conformal factor along with that matrix. And then if I take the coordinate directions with respect to this coordinate system and call them pi, so pi will be the eigenvalue of lambda with eigenvalue lambda I can build an orthonormal basis for the restriction of G out of the pi's, and the images, the images of the coordinates in the codomain under the Jacobian of F. And if I weight these with an appropriate square root of the lambda I and square root of 2, then it turns out what I get is G orthonormal for the tangent space to the submanifold at my point Z. This is Z equals XF of X. And you can by rotating, you can simultaneously diagonalize S, and you'll get some eigen, you need to normalize. And the eigenvectors of S with this normal, when G is orthonormal, involve, because there's a lambda I in the denominator here and the numerator there, they involve the harmonic mean of lambda I. And so now, since we want the largest eigenvalue of this to be as big as possible relative to G, let's order these guys so that mu n is the largest one about them. And then I exploit the multilinearity of the Riemann tensor for G hat. And I get that the Riemann tensor in the EI-EN plane is bounded below by things involving the harmonic mean of the ratio of the lambda I to lambda n. And so these are the crucial terms. And they come with a factor kappa in front because the Riemann tensor was bounded below by kappa times the EI wedge EN squared. And then there's some other terms where you have, instead of 2 PIs and 2 PI bars, you have maybe 4 PIs, or 4 PI bars, but those can all be controlled from below in terms of mu n and some large constant again. And so then you apply the domination of the arithmetic by the geometric mean to replace this sum. I want to sum this over I counting from 1 to n. And I want to say the sum of the lambda i's are, after I take 1 over n of that, is less than the product of the lambda i's to the 1 over nth power. And but I only read because I only really sum from 1 to n minus 1. I have an n minus 1th power here because basically the Riemann tensor vanishes when EI equals EN. And so on the other hand, this is the product up to n minus 1. I want to put in the last, so I want to put in the lambda n here and the lambda n with the 1 over the nth power in the denominator, because this is the product that's given by I want to say the ratio of rho to rho bar. It's the determinant that's controlled. And so, so after you do this, you get a lower bound for the sum, for the partial trace of the Riemann tensor. And because of this extra power of lambda n, you end up with a superlinear term in mu times this coefficient kappa minus all of these guys. And our corollary much earlier said that this was bounded above, or this partial trace provided a lower bound for the restriction of S, so for mu n. And there's a C phi minus 2 here. And the point is that now mu n can't be too big because I have this superlinear thing growing like maybe 1.3 or 1.15, and this linear thing, and that's an a priori estimate on mu n in terms of these constants that appear here and there. And so that a priori estimate is the thing that tells me that my submanifold never gets too close to being vertical. And because mu n is lambda n plus 1 over lambda n, it never gets too close to being horizontal either. So that uniformizes the ellipticity of this equation, and then I get higher regularity by continuity method and shadow theory. And I have come to the end of what I wanted to say. Here are the references. This is the recent work with Brendel, Leger, and Rankin, and these are the older papers with Kim and Warren, and then I wrote a survey of part of this work in 2014. And I can mention that my colleagues Tristan Collins and Fried Tong have begun thinking about the boundary case in conjunction with an application that they have in mind to the Tian-Yau conjecture in complex geometry, Kähler geometry. And so they've discovered a monotonicity formula for the maximal submanifold in this setting that allows them to apply methods that are more familiar from the plateau problem to show regularity in this context. Thank you very much. That's where I will stop.
Okay, so questions? Here, people, well, there is one, but.
Hello.
Hello.
Hello, Robert. Thank you so much. I had a question, and
Yep.
I'm going to apologize in advance because I'm new to studying everything in optimal transport, so maybe I don't have the concepts very clear right now.
Yep.
But I was wondering because the regularity you are asking for the measures,
Yes.
you're asking them to be absolutely continuous, and I'm assuming that also the density has to be smooth.
Yep. So let me go back. Basically what I sketched is the essential ingredient to proving this theorem. So these are the densities. They have to be bounded away from 0 and infinity, and they have to be CK alpha for k bigger than 2.
Okay. So this so everything you talked about cannot be, like, I don't know, interpolated for discrete measures or things like that.
I don't think so. Yeah, no, everything I talked about can't. I wouldn't know how to interpolate it for discrete measures. I mean, so I did mention there's this result of Lopere that says if log rho and log rho bar are at least L infinity, then it's still true that f is C0 alpha. And in fact, the sharp Lopere showed alpha for dimension -1, and the sharp value. The sharp value was shown by Jiakun Liu in his PhD thesis in 2008. So I can't do discrete densities, but I don't need this much smoothness. I mean, sorry, this is different techniques now, but people don't need this much smoothness. Using other techniques, if you have just bounded densities that are bounded above and below, you get Holder continuity, the optimal map. And with a known exponent. So the exponent is known, but that requires A3 strong. If you only have A3 closure, then the exponent is not uniform, but it rather depends on the L infinity norms of these constants. So that's the case. So it's interesting that the case Bx, the bilinear case or the quadratic cost, is actually, A3 is a sectional curvature condition on the cost, and that's for sectional curvature positivity. This guy only has non-negativity. So it's not in A3, it's only in A3 closure. And so for this guy, you don't get this Holder exponent. You only get a Holder exponent that depends on the ratio of rho to rho bar, the magnitude of the ratio of the logarithm of rho to rho bar. So that somehow,
Oh, okay.
yep, the original cost for which the original regularity theory of Delanoë and Caffarelli and Urbis was developed is a borderline case in the Maude-Schrödinger-Wang theory. And you can perturb this cost to make it better behaved. You can also perturb it to make it worse behaved, and then you get these discontinuities for smooth. Then you can, yeah, as I was saying, there are these discontinuities if you perturb this cost in a bad way.
Okay, so but then the measure always has to be absolutely continuous with the Lebesgue measure, right? I mean,
yeah,
this doesn't work if I consider the Hausdorff measure, for example, or things like that.
Right. Yeah. Okay. So I have some not particularly well-known work with Gangbo in 2000, and then with a student about a decade later, Maria Socio. I'm going to say around, I don't remember, 2012 maybe, where we're able to consider measures that live on boundaries of sets. So I can take mu to be a probability. So I take my convex domain omega, and I look at my probability measure on the boundary of omega and say mu is absolutely continuous with respect to surface measure on the boundary. And same thing with nu. And or mu bar. And then first of all, there are examples where you don't even have maps anymore. So for example, a nice example of this is take the unit circle, think of a measure which is mostly concentrated at the south pole, but mutually absolutely continuous with respect to surface measure. Take your target to be a measure which is also mutually absolutely continuous with respect to surface measure, but mostly concentrated at the north pole. And in this situation, you can show that the if you minimize integral, let's say x minus y squared d gamma, gamma having constrained marginals mu and mu bar, you will get an optimizer. It will be unique, but it will not be concentrated on the graph of a single map. It will be concentrated on a union of the graphs of two maps. Because essentially what you have to do is a certain fraction, the mass here has to split, and a certain fraction has to cross the lake to compensate for this. So I take this measure, which is concentrated mostly here, and I'm mapping it to one concentrated mostly here. I would like to stay close to the diagonal, but I can't do that. And so a certain fraction of the mass has to cross the lake. And then after you've corrected this imbalance, the rest of the mass is concentrated on a diffeomorphism that stays close to the diagonal. And in these papers, we're able to show that this guy is a homeomorphism and even a Holder continuous homeomorphism. And actually, we're not able to show this diffeomorphism. And the reason we're not able to show it's a diffeomorphism is that in these places where the mass is splitting, we still have bounds above and below. Maybe even bound on below is tricky because who's to prevent all the mass from going to the other side or 0% of the mass? But we certainly don't know anything about the smoothness of how the mass splits as you vary from one point to another in here. And so, yeah, so you get this kind of picture where you have a graph of two maps, one of which is a homeomorphism. This is assuming both the boundaries are convex, and the other one of which is continuous, but you can't, as far as nothing more smooth than that is known. And again, this is just the case where you have these absolute continuous measures with respect to surface measure on domains. I still see some hands up. Or yeah, I hope.
Yeah, thank you very much.
Yeah. It's interesting. Maybe I make one more comment. It's interesting to note that this paper actually precedes Maude-Schrödinger-Wang, and for us, the convexity of these domains is what ensures the analog of the A3 condition. That in fact, we had to get these regularity, the continuity results in higher dimensions, we need to assume uniform convexity, and that's somehow it anticipates Maude-Schrödinger-Wang's A3 condition in some sense.
Okay, so there is also one hand raised for someone.
Is Samuel Mercer?
Thank you very much. Can you hear me, by the way?
I can, yes.
Yeah. Thank you very much for the interesting talk. I'm interested in sort of as a general question, regarding regularity of optimal transport maps and things connected to that. Post Ma, Trudinger, and Wang, what do you think are sort of the interesting questions to look into regarding questions of regularity for like future research?
Well, okay, so I mentioned one here with these measures that are concentrated on lower dimensional subsets. In that setting, there's also if in the setting I talked about today, if you have a cost that satisfies, for example, A0, A1, maybe A2, but violates A3, there's still a partial regularity result by De Filippis and Figali, which says that there's a closed measure zero set outside of which the map is smooth. And I think questions like that in this unequal dimensional transport are very interesting. And so this is a case where I'm mapping n-1 to n-1, but I could also take absolute continuous to n-1. That would be an example of unequal dimensional transport. And there's a general theory of this that I started with Chapuri and Pass about 10 years ago for mapping like 3 dimensions to 2 dimensions or 10 dimensions to 8 dimensions. And you still get an equation which is kind of elliptic but less local than in this equal dimensional case, because typically you'll have fibers here that are mapping to points over there, and the direction of the fiber will correspond to the tangent to the surface over here. And it would be very fascinating to have a partial regularity result for that. I don't in the case where the target is one-dimensional, I have something like that with Brendan Pass, but for targets that are higher than one-dimensional, it's rather tricky. But you write the equation on the lower dimensional subset, the lower dimensional side, and then it's a little bit non-local on the higher dimensional side. It still has the ellipticity.
Okay, thank you. And similar to something you mentioned earlier, in these settings where you're forced for the transport map to have discontinuities, is there a theory of, say, like BV regularity in this setting? Is that something people have worked on?
Okay, so what people have worked on, so yes, things are BV automatically because okay, so let me go ahead here for a second. I want to get back to, yeah. So this condition here, for example, when B is bilinear and you don't have this term, it's telling you that U is a convex function. And the map is gradient of a convex function. Gradient of a convex function is automatically BV.
Oh, okay.
When you do have B here, you're still a semi-convex function, so the map is still automatically BV. It's very interesting to think about the smoothness of the discontinuity set. And a few things have been written about that. I can mention work that I did with Kitagawa in 2017, but also there's been follow-up work by Jiakun Liu and my former student Xibing Chen, and some of it may involve Wang. I don't think so, but I think it's mostly Chen and Liu, Xibing Chen and Jiakun Liu, on the smoothness of the discontinuity set when you have discontinuities. But typically you have to impose some structure, like at least in my work with Kitagawa, we said, suppose you have a domain, it's mapping into a union of 2 disjoint convex sets. Then we can say that the discontinuity set where you have the tear between the 2 convex sets is differentiable with a Holder normal. And I think that these guys can give you one more derivative. They can tell you it's C2 with a Holder second fundamental form or something like that.
Okay, it sounds very interesting. Thank you very much.
Okay, so I think that there are no further questions, so let's thank Robert